This work has been made in collaboration with some young researchers, Luca Lanzoni and Andrea Sulfia from the University of Modena and Reggio Emilia. We studied in this work the pullout behavior of synthetic fibers treated on this surface with nano silica in order to increase the bonding characteristics and then subject to pullout test. As well known, the addition of steel or polymeric fibers to the concrete mixture increase the strength, the toughness and the durability of the concrete. And these fiber reinforcing concrete find a lot of application, especially in civil engineering, for industrial pavement, precast element, or structure in aggressive environment, such as marine structure, or for earthquake structure, or for structure subject to earthquake loading, where a large amount of energy dissipation is required. With respect to the steel fibers, synthetic fiber have the following advantages. They have a better workability of the mixture, or the fresh mixture. They have chemical stability in alkaline environment, and they have no oxidation problem, and they are lighter, and also they have this peculiarity of electromagnetic transparency, which makes be important for some special structure where the steel reinforcement could interact with the electromagnetic waves. However, the main weakness of this synthetic fiber is the poor interfacial bond strength, since polymeric and concrete are two different materials. One is hydrophobic and the other is hydrophilic. So the bond characteristics is quite low. Moreover, they have some viscous relaxation behavior, which should be taken into account, but this will be made in a second step. The addition of fibers to the concrete mixture increases especially the post-cracking behavior of the concrete. Indeed, as soon as the crack opens, the fibers start working, thus giving ductility to the concrete and transforming the concrete from a ductile material into from a brittle material into a ductile material. These are yes. Okay. These are the result of a 3-point bending test. And therefore a larger amount of energy will be dissipated, especially due to the presence of the fibers. However, in order to remedy the effect of polymeric fiber and to increase the bond strength and the abrasion phenomena, we propose a treatment of the fiber surface with silica nanoparticles, which are deposited directly on the surface of the fiber by using a sol gel treatment. This treatment has been illustrated in a previous work by Dimaida and other co-workers. Here we have some images of polymeric fiber before the pull-out test and after the pull-out test. We can see that these two fiber this one is for untreated fibers and the other is for treated fiber. As we can see, the treated fiber has display a much more deeper abrasion phenomena. Moreover, there are some SEM images of treated fiber, of the surface of treated fibers and untreated fibers. We can see that at the micron, this is half micron actually, therefore at nanoscale, the surface displays a kind of roof surface and some kind of insula of silica, nanosilica particles. And then these are the result of experimental tests on treated and untreated fibers with different embedded length for 2 centimeters and 3 centimeters of embedded length. We see that the solid and thicker line concern the response of treated fiber, whereas the thinner lines is the response of the untreated fibers. What we can observe is, of course, that the pull-out force increases with the embedded length. So from 2 to 3 centimeters, the pull-out load increases remarkably. But we also saw that the peak load, the maximum load of the pull-out load, increased about 2 times between treated and untreated fiber for both embedded length. Moreover, the area under the pull-out curves, which correspond to the energy dissipated during the pull-out process, increased about 3 times between untreated and treated fibers. Therefore, we show that the treated fiber display a remarkable slip hardening behavior of the bone strength. The bone strength increased remarkably with the slip, with the displacement of the fiber. And therefore, slip hardening interface is a desirable property because it's accompanied by a large energy dissipation. In this work, we study actually a one-dimensional model for the pull-out, for simulating the pull-out process of different kind of fibers, not only polymeric, but even steel or glass fiber, which is able to account for the enhancement in the adhesion mechanism given by the surface treatment. And finally, the model is validated by comparison with the previous pull-out result. The model is based on the following assumption, actually. The polymeric fiber experience a large deformation, so finite deformation of the polymeric fibers, and the matrix, the cement matrix, we neglect actually the deformation with respect of the fiber elongation. So the matrix, the cement matrix, is considered almost as rigid. However, we introduce a frictional interface constitutive model between the matrix and the fibers. This model displays an initial linear elastic behavior between the shear stress and the slip distance, and further a slip hardening or softening behavior in the debonding stage, depending on the kind of fibers. Therefore, we were able to develop a one-dimensional phenomenological model, which of course neglects the Poisson effect, the three-dimensional effect, which is not relevant for this kind of test, for pull-out. Actually, yes, the most important character, feature of the pull-out test of synthetic fiber is due to the slip hardening or softening behavior. These are the works related to the current presentation. In particular, the slip hardening model has been developed, proposed initially by Lee and his co-worker, and studied by numerical method. Actually, the experimental test has been made by co-worker of the University of Modena and Reggio Emilia for treated fibers, and then some application has been recently proposed to study the load carrying capacity of industrial pavimentation, for instance, or slab made of FRC, fiber reinforced concrete, on elastic subgrade. Here is the scheme of the test, of the performance test, and we look carefully at the embedded part of the fiber. We refer to an initial configuration, undeformed configuration, and which has a part of the fiber, the inner part of the fiber, which is bonded perfectly to the cement matrix, and the bonding part starting from the loaded end of the fiber. And we also correspondingly we consider a deformed configuration where we set the balance condition, balance equation, and we denote with as the slip plus distance and with tau the interface shear stress, and these two variables are related by the interfacial constitutive relationship, which is drawn, which is sketched in this slide actually. We have initially, for the interface constitutive model, we assume an initially linear elastic behavior in the bonded part of the fiber. Then the behavior is different for synthetic fiber of steel fibers. Synthetic fiber display a slip hardening behavior in the debonded part due to the abrasion of fiber surface and accumulation of wear debris. On the contrary, steel fibers display a slip softening behavior or constant frictional stress, and the slip softening is mainly due to the breakdown of cement at the fiber matrix interface. This is the analytical representation for the linear part of the interface constitutive model and the slip hardening or softening part behavior, which is modeled by a simple parabolic quadratic relation between shear stress and slip distance. So, by imposing the balance condition on the deformed configuration, we obtain a second-order nonlinear differential equation where this term is different for the bonded and the bonded part of the fiber. However, this relation can be integrated actually 2 times, and this is the Lambert function which appears in this integration, and this term is different for bonded and the bonded part of the fiber. However, they can be integrated analytically. Sorry. Okay. So we can find imposing the boundary condition at the end, both ends of the fiber, at the section between the bonding and the bonding part of the fiber, we can obtain closed form solution for each stage, for the elastic stage, for the debonding stage, for the final pull-out stage. We can obtain the relation between the pull-out load and the displacement of the fiber. And these are some results actually. We can see that the theoretical curves approach reasonably well the experimental result, both for treated and untreated fibers, and for both embedded length of 3 and 2 centimeters. So the model has been validated, and the parameters which define the interface constitutive model has been validated by the experimental result. And then we also applied this formulation to study the load carrying capacity of fiber reinforced concrete slab on elastic grade, and we find analytical expression of the collapse load, and we approach, actually we compare it with previous approximated or empirical formulas obtained for the definition of the collapse load. In conclusion, we see that the model predicts accurately the experimental result, both for treated and untreated fibers, and the slip hardening behavior, actually the last part of the pull-out curves, has a more relevant influence on the behavior of the pullout more than the elastic stage, the initial elastic stage. Actually, in a simplified model, the initial elastic stage can be actually neglected, or with respect to the pullout stage. And the model is able to consider every kind of fibers, just changing the interface constitutive law. And the parameters are found to be independent from the geometry, and the material parameters are found to be independent from the geometry and loading condition. However, the material parameter might depend on the treatment performed on the fiber surface. And in order to define this parameter according to the special treatment, a further investigation of the basis of the adhesion mechanism based on a micromechanical approach might be required. This model can be used also to study the bridging crack, the crack process in fiber reinforced concrete, actually. Thank you for your attention. If there is any question.